is one of 2 true celebrities in our lecture series this year. And by true celebrity, I mean he has a persistent Wikipedia page. So, he has a BS in Physics and Mathematics from the Rose-Hulman Institute. Where is Jesse? Jesse's a Rose-Hulman person. My son is too. He has an MA and PhD from Rice University. He spends most of his time at Fermilab or at CERN. He used to work at, still works a little bit at D0, co-discoverer of the top quark. And he works at CMS, co-discoverer of the Higgs boson. He's coordinated lots of scientific papers on these subjects. He's written 2 books, and a 3rd one is on the way. The first book is Quantum Frontier. The second book is Understanding the Universe. And the 3rd book is about aliens. He's authored many magazine articles in Scientific American and elsewhere. He has an extensive blog, YouTube videos, and several columns on Fermilab Today, which you should read all the time. He's had a couple of TED Talks, and you can see those online. Those are very interesting. And in 2013, this year, he received the European Physical Society HEPP Outreach Award for communicating in multiple media the excitement of high-energy physics to high school students and teachers and the public at large. So I think we're in for a very interesting and entertaining lecture. Dr. Lincoln.
Nothing like building me up there. Now I can actually do it. Okay. Cool. Okay, so is the audio good, even in the back? All right. So, as Elliot suggested, my name is Don Lincoln. I'm a physicist here at Fermilab. I do split my time between working on the Large Hadron Collider as part of the Fermilab research contingent. I've also spent some time recently working on the Fermilab-based program. We have an experiment called Mu-to-E, which I'm doing a little bit of work on, building or designing some of the technology. And I do a lot of writing and talking to the public because I think it's important. And hopefully some of that will rub off and maybe you'll get something out of this. So let's start out with this. We start with this by pointing out that the universe is a very beautiful place, whether it be the beautiful flower, the spiral galaxy, the sunrise. But in addition to this beauty, these things all seem very different. I mean, what does a flower have to do with a person, have to do with the galaxy? And that brings us to the second kind of beauty. The second kind of beauty tells us that everything you see in the universe is made of a few simple fundamental building blocks. Now, this is a question that has bothered thinkers for as long as people have been writing things down, of course, probably long before that. We now know that everything you see here can be created as a mixture of these 2 particles, called up and down quarks, an electron. You take an up and down quark, you can make protons and neutrons. You add an electron, you can make atoms. If you take atoms, you can make everything. Over here, we have the force particles. There are 4 forces. We'll talk about them in a little bit. But these particles are the things that hold the quarks together in all of these very complex configurations. So in addition to just the sort of aesthetic beauty of the universe, there is a fundamental beauty, a sort of mathematical beauty, an architectural beauty, that this little bit of building blocks makes up everything. Now, for those of you who, not all of you have studied all of the physics we do here, so I thought I'd give you some sense of the various scales we have. So the smallest living thing is a virus. Now, my wife, she's a biology teacher, and she tells me, but, Don, viruses aren't really alive. And it's true, she's right, but she's not here. So the virus is the smallest living thing. And a virus is 10 to the minus 7th meters. So this is about a meter. You guys know how big a millimeter is. You can take 10,000 viruses, put them side to side inside a millimeter. That's crazy small. You can't see those. But this is huge on the scale of the things that we study here at Fermilab, or for that matter, at any sort of physics laboratory. Viruses, of course, are made of molecules, which are 1/100th the size of the virus. Atoms are about 1/10 the size of the molecule. This sort of picture of what the atom looks like with the nucleus and electrons swirling around the outside, that's a little outdated, but it's close enough for what we need to do. The center of the nucleus, here with the protons and neutrons, this is 10 to the minus 14th meters, which means the nucleus is as small to a virus as a virus is compared to you. And yet studying this is like so 1930s. I mean, this is like 80 years ago. Nobody does that anymore. I guess some people do that anymore, but not the cool kids. So protons and neutrons, we know about those. They were discovered in the 30s, the 20s and 30s. We now know that protons and neutrons themselves are made up of even smaller particles. These things, there are 3 of them, they're called quarks. Here. A quark, you can't see that, but there's a little less than sign. A quark is smaller than 10 to the minus 18 meters. That means it's smaller than 1,000 times smaller than a proton. And this number is actually wrong. It's not 10 to the minus 18 meters. It's now a little bit lower than 10 to the minus 19 meters. And the reason I know that is because people at CERN, myself and my colleagues, are constantly pushing that number, making it smaller and smaller. So why do I have less than and not a size? What I know is I know what things my equipment can see. And my equipment can see things 10 to the minus 19 meters, 1/10,000th the size of a proton. And I look at quarks, I don't see any size. So either quarks are zero size, but all I really know is they're smaller than 10,000 times smaller than a proton. Now quarks are well understood. They were postulated in 1964. They were discovered, proven, with no question, in the 1970s. So this is real. So here's particle physics now. What is that next building block? And the story of this ever-decreasing size, as I said earlier, is the sort of final chapter in the story that's been going on for thousands of years, trying to understand the fundamental building blocks of the universe. So high-energy physics is the study of the smallest bits of matter, but it also investigates sort of the deepest and most fundamental aspects of nature, how these things are held together. We here at Fermi and at CERN can look at things, understand the nature of the universe immediately after the Big Bang. We can recreate the conditions of the early universe in our experiments, and I'll explain that in a little bit here. And so we can see temperatures that we haven't seen generally in the universe for 13.7 billion years. That's actually 13.8. I didn't change it. That changed about 6 weeks ago with some new measurements. So that's one of the things that's kind of interesting. Everything I tell you here we know, but some of the details, this number and this number, they change because we are, after all, on the research frontier. We're learning more all the time. So give me a little quick reminder of all this. So the periodic table was invented in the 1860s, and that was an amazing simplification of the universe at the time because we saw that with 100 elements we could make up all of the matter that we were familiar with then. And in the beginning of this century, or I guess the last century now, we now know about the protons, neutrons, and electrons that make up atoms. And so it's amazing. 3 building blocks make up the universe. Well, you know, physicists don't know enough to leave things well enough alone, and we now know that protons and neutrons actually are made up of other things. So a proton is made up of quarks. It's made of 2 up quarks and a down quark. A neutron is made of 2 down quarks and an up quark. Electron, to the best of our knowledge, has nothing inside it. So here is the current periodic table. This is what we think of now. So I'll give you a little bit of orientation. You remember from chemistry that the columns here are chemically similar elements, so hydrogen, lithium, sodium, and so forth. These are all highly active elements, whereas the noble gases, helium, neon, argon, and so forth, are not interactive. But the columns are sort of what we call chemically similar. This is sort of it's a similar thing here, except it's the rows. So up and down quarks are what you need to make up protons and neutrons. But you have this thing called a charm quark and a top quark. And a charm quark has the same charge as an up quark. A top quark has the same charge as a charm, the same as an up. So these rows are kind of equivalent to the columns of the periodic table. You take the up and down quarks and the electrons, and you can make matter that we're familiar with. There are these things called neutrinos, which I don't have time to talk about, but you'll have lectures on that from someone else. So you might ask yourself, if all I need is up and down quarks and electron to make atoms and make everything, why do we have these other columns? And the answer is, I don't have a clue. Nobody has a clue. Drives me nuts. But remember, in the 1860s, we knew about this periodic table, and then we subsequently discovered that the chemical similarity had to do with how the electrons were arranged around the atoms, and the size had to do with more and more protons and neutrons at the center of the atom. So this was the first indication of something inside elements, and the fact that we have chemically similar things is probably the first indication that something's going on inside of that, but I don't know what it is. I really wish I do. If you get any ideas, you let me know, and we'll share that money from Stockholm. Now, the up and down quark and the strange quark we knew about before quarks we knew the quarks existed. So these were invented in 1964. Charm quark was discovered in 1974 simultaneously at Long Island in California. Bottom quark was discovered at Fermilab here by Leon Litterman, the second director of the lab. He wasn't the director at the time. So 1977. Top quark was discovered here at Fermilab by me. Well, okay, it was me and so 800 of my closest personal friends, but I'm not taking credit for it. Shh, don't tell my mom. She thinks I did it. Okay, down here you have the electron. You know what the electron is. The muon is like a heavy electron. A tau is like a heavy muon. Why are these things? I don't know. But there's something being told there, and that's something I spent some time thinking about. There are four forces of which we're familiar. They are gravity, which holds us on the ground. There's electromagnetism, which makes light work. It makes, of course, electricity. It makes magnetism. It's why I can't put my hand through a wall. The electromagnetic force keeps me from doing that. There are two forces that you're less familiar with, the strong nuclear force and the weak nuclear force. The strong nuclear force holds the nucleus of the atom together. The weak nuclear force causes some parts of radioactivity. If you list them in orders of strength, the strong nuclear force is the strongest. If you just call it as unit 1, like 1 pound or 1 mile or 1 whatever, the electromagnetic force is between like 100 and 1,000 times weaker than the strong force. The weak nuclear force is 100,000 times weaker than the strong force. And gravity is on the order of like 10 to the minus 40 times weaker than the strong force, which means we can't understand gravity in our big particle accelerators. Each one of these forces comes with a particle that's been found. Gluon was found in 1979. Photon was discovered at the turn of the 20th century. W and Z bosons, the particles of the weak force, were discovered in 1983 and 1984. The graviton, there's a question mark there. Nobody's seen a graviton. There may or may not be such a thing. So this is sort of a real quick whirlwind through particle physics. And now I'm going to sort of bring us through the cosmos and then back to the energy frontier, which is after all why you're here. So, about 14 billion years ago, the universe began in a cataclysmic explosion that we call the Big Bang. Since then, the universe has been expanding and cooling, leading to the familiar night sky that we see today. Scientists and philosophers have long wanted to understand in detail the origins of the universe, how that universe came into existence. And of course, this has eluded us for hundreds of years. It's been impossible. Well, until now. It turns out it is possible to turn back the clock and recreate the conditions of that early maelstrom. And to do that, we do that with our accelerators. So at Fermilab and at CERN, my colleagues and I collide subatomic particles traveling at nearly the speed of light and make these big collisions. The temperatures at the center of these collisions is incredible. It's 100,000 times hotter than the center of the sun. It is 10 times hotter than the center of a supernova, which is the explosion of a star that is so amazing, so cataclysmic, and so bright that you can see it across half the universe. And so you might be asking yourself, that sounds really hot. I mean, should they be doing that? But in order to understand that that's an impressive number, but it's not dangerous, you need to talk about mosquitoes. So what do these have to do with each other? Well, the thing is that the collision of two protons inside the Large Hadron Collider is exactly the same energy as these two mosquitoes crashing into one another. That's the energy of a Large Hadron Collider collision. And so I know what you're thinking. You're thinking, what do you do? But now you have to ask yourself, how can I be telling you the same thing? I'm telling you that it is 100,000 times hotter than the sun or the sun, and I'm telling you it's two mosquitoes bonking into one another. Like, come on, what's going on here? The thing is, that energy of those two mosquitoes crashing into one another is much, it's in a volume, tiny, smaller, much smaller than a proton, thousands times smaller than a proton. Now, to give you a sense of what it's really like at the center of these collisions, I need to invoke the power of the sun. Now, I don't mean the sun when you go outside and burn yourself when you're swimming on the beach. You know, that's great. I don't even mean the amount of the sun, the energy of the sun hitting the earth. I mean all of the energy of the sun, every single bit of it. And I don't mean for a day, a month, a year. You need to take all of the energy of the sun for 1 million years, collect it, store it, and concentrate it into a volume the size of a basketball. Shrink yourself down to the size of a pea, jump inside a basketball, and that's what it's like at the center of these particle collisions. At these temperatures, energy and matter lose their identity with energy converting into matter. and matter converting back into energy, just like Einstein said over 100 years ago. This really is the very cauldron of creation, the very foundry in which the universe itself was forged. If this doesn't make you at least proud and a little bit humble, but really proud of your humanity, then I don't know what will. This is truly amazing that we are able to do that. So here I just have the same things I told you before. Energy ATV, that's what we're doing at the Large Hadron Collider. It's a crazy temperature, 100,000 times hotter than the sun, and you need a million years of the sun in that big a volume. Pretty cool. And with that, I will now bring you to the Large Hadron Collider. So the Large Hadron Collider is the biggest particle accelerator operating now. Here we have a photograph of it, segueing into an engineering picture so you can get a sense of what it looks like. This ring, here is CERN, actually this little triangle-shaped thing you can barely see. That's CERN right there. This big ring here is the same size as the Fermilab accelerator that you see from the 15th floor. The actual LHC accelerator is 18 miles around, swooping across the French countryside. To give you some orientation, here it is in Europe, and it's not that big. Sometimes I have to tell people that. This is what it really looks like. So this is Lake Le Mans, which is a lake right outside Geneva, Switzerland. Here is Geneva, Switzerland. Right there, in case you're wondering, is the Chocolaterie de Mont Blanc, which has the most expensive but really most awesome chocolate in the world. So if you go there, make sure to stop. And no, I don't get a cut. Here is the Geneva airport, and there's the CERN accelerator. And that ring is the size of the Tevatron. Here's another picture of it. This is completely misleading because the aspect ratio is all off. The ring is 18 miles around, whereas the depth of their various experiments are about 300 feet underground. But that kind of gives you a sense of where it is. Most of the LHC is in France, some of it is in Switzerland. Now, I've said that there are experiments there. There are, in fact, 4 experiments: LHCb, CMS, ALICE, or ELISE, and ATLAS. So I'm going to concentrate on 2 of them, but here they are. So the first tell you about the little ones. The one experiment is called LHCb. Now there is an interesting thing in the universe. You guys all heard E equals mc squared that says energy can be made into matter and matter can be made into energy. But really what happens is when energy turns into matter, it makes matter and antimatter in equal quantities. The universe was once hotter and smaller, and so when that universe was cooling off after the Big Bang, matter and antimatter were made in equal quantities. But you're all matter, I'm matter, everything's matter. So where did the antimatter go? The answer is we don't really know. This experiment is designed to look into that. The ALICE experiment is kind of cool. They collide nuclei of lead, 208 protons and neutrons, 208 protons and neutrons, smack them together at such energies that the protons and neutrons actually melt and the quarks scurry around willy-nilly. And that's looking at things called quark-gluon plasma, and that's pretty cool. Give you a sense of scale, there's a person right there, so this is a big experiment. However, the 2 biggies are over here. So the smaller of the 2 experiments is the CMS experiment. That's something that Fermilab is involved in. Here the beam would enter at this point and enter at this point and collide there at the center of the detector. This thing is huge. It is 50 feet by 50 feet by 70 feet. It weighs 14,000 tons. And to give a sense of scale, there's some people there. This sucker is really big. The biggest of the experiments is the ATLAS experiment. It is 70 feet wide, 70 feet high, 140 feet long. That means that if you took 4 of those, they would just barely fit on Chicago Bear football field. Just enough room left over for cheerleaders on the side. This sucker is really big. It is 9,000 tons, and here are pictures of people there, and there are 2 more up there. So this thing is really, really big. On the other hand, Fermilab doesn't work on this, so we all know which one is the good one. Okay, so here are some pictures of that. Compact beam on solenoid, 50 feet by 70 or 80 feet, 14,000 tons. These white dots here, boom, 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 boom. Those are guys' hard hats. These are people. That's the experiment. ATLAS is much, much larger. It's 70 by about 150 feet, 8,000 US tons. I don't have a person in there, but this thing is absolutely enormous. One interesting little factoid is if you were to take this thing and wrap it in plastic, its density is actually lower than water, so it would float. I'm not sure why you would do that, but if you wanted to, it's a useful little factoid. And just proof that I really am who I say I am. There I am. Okay, here's CMS. And that's what it looks like. It's this big, amazing, awesome piece of equipment. Now, I want to tell you about some of the cool science that we do, because after all, you know, these are just gizmos. I mean, this is a camera. When you really think about this, all this is an amazing camera. I mean, it's 100 megapixels, which doesn't sound that impressive because you can go buy 10 or 20 megapixel cameras at Best Buy. But these things can take pictures 40 million times a second. So that's a bit of impressive business. So let's start talking about some of the science at the LHC. So the standard model are these quarks and leptons and those forces that I was telling you about. In the simplest version of this, all of those particles should have zero mass. Now we know that's not true. The top quark discovered here at Fermilab has a mass of 170 times the mass of a proton. Real big, heavy thing. So, because particles do have a mass, either the standard model is wrong, or there's something more to the story. And I sure hope there's something more to the story. We've been fooling ourselves for a long time. So in 1964, this dude by the name of Peter Higgs, along with some other guys, put together some ideas that were floating around at the time, and he postulated a field in the universe called the Higgs field. And particles interact with the Higgs field and get their mass. So if that's true, there is this particle called the Higgs boson. And the Higgs boson kind of works well. First the Higgs field, then we'll get back to that. So this is what a Higgsless world would look like. A photon has no mass, and then this is whatever particle you want. I don't care what it is, electron, quark, whatever. In a Higgsless world, there is no mass, so these things are exactly balanced. But if you turn the Higgs field on, what happens is the particle gets mass, the photon doesn't, and they become unbalanced. So that is kind of the gist of the Higgs field. And so there is the Higgs field, there is a Higgs boson, and this is quite tricky. So, the question is there a simple explanation that you guys will be able to understand? Now, I thought about trying to explain this all up here with, writing things on the board and stuff, but that seemed to be, like, it might be very difficult. So, I did what everyone else does, is I went on the internet and I found the YouTube video. Now, this YouTube video explains the Higgs field and the Higgs boson, actually in a pretty good way. So just pay attention, because this guy actually really knows what he's talking about. If you've had any interest in physics, you've heard about a thing called the Higgs boson. But just what is it, and why is it interesting? In 1964, a physicist by the name of Peter Higgs took some ideas that were floating around at the time, added an insight or two of his own, and proposed that there was an energy field that permeated the entire universe. This energy field is now called the Higgs field. The reason he proposed this field was that nobody understood why some subatomic particles had a great deal of mass, while others had little and some had none at all. The energy field that Higgs proposed would interact with the subatomic particles and give them their mass. Very massive particles would interact a lot with the field, while massless particles wouldn't interact at all. To better understand the idea, we can use the analogy of water and swimmers. In our analogy, the water serves the role of the Higgs field. A barracuda, being supremely streamlined, interacts only slightly with the field, and it can move through it very easily. The barracuda would then be similar to a low-mass particle. In contrast, my buddy Eddie, no stranger to donuts, can only move very slowly through the water. In our analogy, Eddie is a massive particle, made massive by interacting a lot with the water. The lightest of the familiar subatomic particles is the electron, while in the subatomic world, the king of mass is the top quark. It weighs about as much as an entire atom of gold, about 350,000 times more than the electron. I'd like to stress that we believe the top quark is not more massive because it's bigger. It's not. In fact, we believe that both the top quark and the electron are exactly the same size. Indeed, they both have zero size. The top quark is more massive than the electron simply because it interacts more with the Higgs field. Actually, if the Higgs field didn't exist, neither of these particles would have any mass at all. Now, in the press, you don't hear about the Higgs field, but rather the Higgs boson. How are these two things related? The Higgs boson is the smallest bit of the Higgs field. To understand how that works, we should again return to water. Everyone knows what water is. If you're immersed in it, you know that water is everywhere. It's a continuous medium, and there are no holes in it. We also know that water is made of molecules, specifically H2O. If If you hold these two ideas in your head with the realization that water consists of countless individual molecules, you can now begin to appreciate the Higgs boson. The Higgs field that gives subatomic particles their mass is made of countless individual Higgs bosons, just like water is made of individual molecules. You should keep in mind that the Higgs boson hasn't been discovered yet. And what I'm describing is simply the most popular idea as to why subatomic particles have the masses that they do. As I speak, my colleagues and I are studying data taken at huge particle accelerators to see if this idea is true. Stay tuned. So, I want to draw your attention to a couple of things. One of which is that I make a bunch of videos, and if you're interested in more of them, you can go on youtube.com/Fermilab, and there's a whole bunch there about antimatter and neutrinos and standard oil and supersymmetry, yada yada. But that's where you can find them. But the second thing I want to draw your attention to is I ended that video saying that the Higgs boson hadn't been discovered yet. And this was actually out about a year before we had the hoopla of the Higgs boson last year. So this was about 2 years old. But there's still some question about the whole Higgs boson thing. And that's what a lot of the rest of this presentation is going to be at. It's telling you what we know and what we don't know. But before we do that, draw your attention to this final thing. So this is the standard model as we understand it. You have the quarks, you have the leptons, you have these force-carrying particles. Everything here has been discovered. The Higgs boson is the quantum of this energy field that permeates the universe and gives the particles their mass. This is currently our best understanding of the standard model, our best understanding of the universe, and everything that I show you here has been discovered, and the Higgs boson has been at least glimpsed and maybe discovered. And I'll explain more about that in a moment. So, to do that, now we're going to get a little more technical. So, the first question you might ask yourself is, how are Higgs bosons made? Well, there are lots of different ways. It's not like you just make a Higgs boson. What we do is the LHC is we take two beams of protons, we slam them together, we convert their energy into matter. But in detail, there are various ways that can happen. For instance, here, you have two gluons, they turn into top quarks. The top quarks annihilate and make a Higgs boson. And the signature would be that you would see a Higgs boson with two top quarks. Similarly, you've got this thing called the WZ Bremsschwung, where you've got a quark and the antiquark makes a WZ, knits one Higgs. So this you see a WZ and a Higgs boson. You have this method here where you make a Higgs boson and two quarks. And then finally you have the one where you just simply make a Higgs boson. Now these numbers here are the relative probability that this will occur. So this is by far the most likely thing. This is 250 times more likely than this guy. This guy is 20 times more likely than this guy. So you'd think, well, we'd look for that. The problem is the Higgs boson decays into two particles, bottom quarks, W particles, or whatever. And it's very easy other ways to make two bottom quarks and two W particles, or whatever. And so that makes it really difficult to actually see these guys. It turns out that these methods here, where you have a Higgs and another particle, or a Higgs and two more particles, these are actually easier to identify. So most of the original work was done using these guys. Now, of course, in order to say that we found the Higgs boson, this was the actual prediction, and so we need to see all of them. But originally, the original work was done here. So now that's how the particles were made. Now I wanted to show you about how they decay. To do that, I need to show you this. And so it's all complicated. I already see the guy back there. He's already texting. Oh my God. But believe me, it's not as complicated as it looks. Trust me, I'll get you through this. Okay? So this decay mass here this is the possible mass of the Higgs boson, and here are the branching fractions. So this is 100%, 10%, 1%, 0.1%. And you get all these possibilities. The top quarks, Z bosons, and W's, got awful lucky mess there. Now, if the mass of the top quark was heavy, I don't care about any of this crap. If it's heavy, here's heavy. Higgs boson would decay into top quarks, W bosons, and Z bosons. So you just look for those and forget about the rest of that mess. If the Higgs boson had a medium mass, well, there's all this stuff, which is very unlikely, but you've just got W bosons and Z bosons. So this is nice and simple, just two things to look at. If it's low mass, well, then there's a lot of stuff going on. Bottom quarks and W's and gluons and so forth. And, of course, the Z boson, the Higgs boson is in that mess. So that's a drag. But it's not such a drag because this gives us lots and lots of handles on it. Remember, Higgs theory is written down with exact predictions. If Higgs theory is right, and the mass is this, you can go up and it predicts exactly what the decay fractions are for all of these things. And if you don't see exactly what was predicted, you're not seeing the Higgs boson, you're seeing something else. So it's really nice that we're actually down here. You have lots and lots of channels that you can get a handle on. But we see, it turns out that the thing that we found is down here somewhere. So bottom quarks is the most likely, W bosons is the next likely, and some other stuff down here. So you think that's what we would look at, but again, the story's not that easy. So the thing we found on July 4th, so almost exactly a year ago, had a mass of 125 GeV. If Higgs boson theory is correct, it should decay in the bottom quark 60% of the time, W is 20% of the time, gluons 9% of the time, and then just a little bit everywhere else. So you'd think you would look for these two guys. However, in the discovery papers, this is where all the action was. 3% and 1%. All this stuff is too hard. Two bottom quarks, if you collide two beams of the proton, two beams of protons at the LHC, two bottom quarks come out like 2% of the time. And this happens like parts per billion compared to other collisions. So the problem is, how do you know when two bottom quarks come out? Are they the boring 2% kind, or are they the parts per billion kind? So this is very, very hard to do. This, however, turns out you can make very, very clean signals. And this gives you a sense. So here is one of the collisions from the CMS detector. And what we see is we see that this is a cylinder, so this is a circle, and this is the long dimension. So you think of this as a soup can. There's the center of the detector. Proton beam entered here, and here, collided there. And all this crud's coming out, all these particles with these yellow lines. But the thing to draw your attention to are these two green guys, right there, and right there. These are two photons. And so what you do is you take those particles, you add up their energy and momentum, and you calculate the mass of the thing that decayed into them. And if you do that, you get this plot. So this is the plot from a year ago, July of last year. And so this green curve here is the prediction of what you expect to see if the standard model is right, but you take away the Higgs theory. So you just erase the Higgs theory, keep all the rest of the standard model, and that's what you see. And you see that in the black dots are the data. So you see good agreement with the data, and then all of a sudden there's too much, and then good agreement with the data. So this is the zoom in right here. So this little bump here, what that tells you is the standard model without the Higgs boson. It doesn't tell you that this is the Higgs boson. It just tells you that there's something beyond the standard model without the Higgs boson. And that's really all it tells you. But that is the kind of quality of the data that we announced a year ago. So let me show you, here's a case where you have Higgs boson decaying into two Z bosons. And then the Z bosons decay into an electron, antimatter electron, and a muon, an antimatter muon. So the same thing, cylinder shape, collision is there. So you have an electron, and a muon, and a muon. And so these are the kinds of events that we needed to look at to find out if we found the Higgs boson. Now the data from this one is even cooler. Okay, so here is the mass of the thing that made those two electrons and two muons. And this is the number of events. So that's number of events per bit. The data are the black dots. The blue curve is what you see if the standard model is right, but there are no Higgs bosons. And what you see is there's very good agreement, and there's a little bit of extra right here, and that red line there is the fit to the Higgs boson, 126 GeV of mass. The thing I really want to draw your attention to is how many events we're talking. That is 4 events, 3 events, 2. So I can do that. 2 plus 2 plus 3 is 7, and 4 is 11. But some of them, this blue curve, are ones that you expect to get that aren't the Higgs boson. So we're talking about 10 events. There are billions with a B collisions recorded, and 10 of them have the right properties. And we claim we found the Higgs boson. That should blow your mind, it does mine. So why could we do that? The reason we could do that is the following. It wasn't just that one plot. If it's just that one plot, you guys should be throwing tomatoes at us and saying that's crazy. But what happened is there are 2 experiments. There's CMS and there's Atlas. And there's data taken in 2011 and data taken in 2012. And for each of these, data taken in 2011, they looked for the prediction to tau decays, W boson, Z's, photons, bottom quarks, and the same thing with everywhere. And what you find is that all of these tell the same story. So it's not that one plot says, there was a Higgs boson. There are here 17 plots, and there are actually more. Each one of these are several analyses. Many, many, many measurements that tell the same story. So, the question you might ask yourself, and you should ask yourself, and everybody asks yourself, was the Higgs boson found at the LHC? And the answer to that is, a new boson was found. We definitely found something. Those bumps say there was something there. Is it the Higgs boson? The answer is maybe. And of course, then that's followed up by, what's the deal, you know? Dude, tell us what you know. Okay, so here's what we know. Remember, there are two kinds of discovery. There's a discovery where you weren't expecting it, like you're walking down the street and you go, holy cow, there's a leprechaun. That's a discovery that blows your mind. It's a real discovery. That's not what the Higgs boson was about. The Higgs boson in 1964, the dude said, all right, Higgs boson, write it down. And I predict this, and I predict this, and I predict this, and this, and this. And a laundry list of predictions. And we're just going to go check them. And if we see all of those, this prediction is right. That's the kind of discovery we're doing here. Now, there are many predictions that were made. I'm only talking about a few of them here. But had predicted properties. Had no electrical charge, had the spin, the quantum mechanical spin is 0, and they predicted there was nothing inside it. Furthermore, it made exact predictions for how it would decay. Well, what have we actually measured as of July of last year? Well, the thing we had found had no electrical charge. We don't know, we didn't measure if it had any spin of 0. We didn't check if it had anything inside it. We measured these guys with pretty good detail. We made some measurement of these guys, but they weren't all that accurate. And that's where we stand. We didn't measure this, we didn't measure this, we didn't measure this, didn't measure this. I mean, these are the things, as of July 2012, what we measured. That is why we say it is consistent with being the Higgs boson, because nothing that we measured showed it to be wrong. But that doesn't mean that it was right. It just means not guaranteed wrong. So here's another yucky plot, which put your phone away. I don't want any of my gods going on. So here's an atlas. Here's CMS. And don't worry too much about much of this, but I'll show you how to understand this in a minute. But this is data measurements. Now, what should it look like? If the Higgs boson didn't exist and everything was perfect, we would see the data along this left-hand line. Now, real measurements don't look like that, but if everything was perfect, if it was a freshman college physics class, that would be the answer. If the Higgs boson existed and it was exactly as predicted, we would find the data on the right-hand line. And again, CMS and atlas. So that kind of tells you what you should be looking at. The final thing I want you to remember is what those error bars mean. Those error bars that we're talking about, that says that there is a 70% chance that the real answer is inside that range, which means there's a 30% chance that it's outside that range. And that's how they interpret this. So now we go back to that. So we have, when we have small error bars, we find that it's consistent with the right-hand side. These guys here, it's in the middle, it's halfway between the two, but it's got big monster error bars, which means there's 70% chances between here and here, which means, yeah, it could be here, but it could be here. That's why I said these were not really well measured back in July. If we go over here and look at CMS, what we find is this is measuring a little low, but certainly with the uncertainties, it could be here, could be here. This one's a little bit high. There's a 70% chance that it's in here. Well, okay, so that means there's a 15% chance here, 15% chance here. 15% chance is reasonable. Down here you've got, oh my gosh, this is consistent with being 0, but it's got huge error bars. So it could be all the way up here. That's not a very good measurement. And this is what we had talked about. But so if you have to really learn statistics, if you're going to do particle physics, you have to take this kind of data and come up with an answer from it. And the answer is that this is quite what you'd expect if the Higgs boson were real. So that is July of 2012. So what's new since July of 2012? Well, we've made more measurements. They're more precise. We've studied the spin of this new particle. We've studied the parity of this particle. You might ask what parity is. I'll explain that just a little bit in a minute. So let's look at the precision. So this is the July 2012 measurements. These are now just the CMS measurements. And that's only because I happen to have easy access to them. The Atlas measurements tell the same thing. So you see that there's a handful of measurements with big uncertainties. Now the measurements are much smaller. I should say the precision is better. The errors are smaller. So Higgs to Z boson should be somewhere here. Higgs to W's is really tiny error bars. The ones that are way off, like this one, they have big uncertainties. What this is telling you is as we get more data, the measurements are looking more and more like they're consistent with a right-hand line, which is what they have to be if it's the Higgs boson. Now let's talk about spin. The thing that we found in July had two possible spin states. One is spin of 0 and one is spin of 2. Remember, a spin of an electron is a half, spin of photons and gluons and so forth is a spin of 1. Spin 0 is predicted, spin 2 is possible. So how can you tell the difference in the spin? Well, if something isn't spinning, then it has an interesting property. It means if you take that particle, you put it in deep outer space, there's nothing to give it a direction. I mean, all directions are totally equal. And so consequently, if something has spin 0, the particles should come out in all directions with equal probability. And if they don't, then it's not spin 0. Now, if you have a particle with spin 2, I mean, it doesn't really spin like this, but this is kind of a good, mental image. It has an axis. Since it has an axis, there is one direction that's different than all the other directions. And so consequently, if you look at the direction that the K products come out, the fact that there's a spin axis will give you a preferred direction. And so that's the measurement there. And what we found is, this is what's predicted, this is what we found. And this is possible, but the data didn't agree with that. The thing that we found is spin 0, so chalk went up to the boson. Now here's parity. Parity is what happens when you swap left for right. So here you got a kid, two hands up, one hand down. If you swap left and right, what happens is still two hands up. But now, instead of having a right hand up and a left hand down, we have a left hand up and a right hand down. So if you swap the parity, this is different and this isn't. And this is called positive parity, and this is called negative parity. And actually, how we study that has to do with some very complicated things involving angles. But this is the gist of it. We're studying how the Higgs boson handles reflection in space. Does it look like this, or does it look like that? So we studied the spin and parity. This 0 plus means spin 0 positive parity. That's what's predicted. In the measurements, now this is March of last year. We're only talking a couple of months ago. We tested 0 plus, or minus, 2 plus, 2 minus. And even though the thing that we discovered in July of last year could not possibly be spin 1, we tested that too because, well, why not? Might be some mysteries there. And what we found is that O positive. It's not a blood type unless it's the Higgs boson blood type. What we found is consistent with the Higgs boson. So we have two more bits of information that says we should believe that this is looking more like the Higgs. And well, that's what I said. Okay. So now, if you've been listening in the press since March, there's still this question about the Higgs versus a Higgs. The standard model predicts one Higgs boson with some of these properties I've described to you. The problem is there's an extended theory called supersymmetry, and it predicts a particle exactly like this particle. So, did we find the supersymmetry thing, or did we find the standard model thing? Yeah, they're exactly the same. Well, there's something that might help you, and what helps you is that the extended supersymmetry theory predicts 5 Higgs bosons, not 1. But we've only seen 1, so are we good? Is this it? That's it? Okay, so we're happy. Except, there's no guarantee that these guys all have the same mass. Suppose these 4 Higgs bosons of supersymmetry are above the mass threshold that we found, and all we found is just the 1. There might be 5, and we only found 1 of them. We don't know. So that's why we talk about finding a Higgs boson versus the Higgs boson. We have certainly found something that acts, smells, tastes, and looks like a Higgs boson, and it may be the Higgs boson. We're going to have to kill these to be sure that we didn't find this, which is a possibility. So what are some of the consequences of the Higgs boson? One of the questions people have been talking about is, does the Higgs boson, the mass that we found, have any consequence for the fate of the universe? It's kind of dramatic. So to know that, you need to understand 3 terms: stable, unstable, and metastable. And to do that, we've will involve, of course, billiards and bars. So if something is stable, pool cue is stable. Put it on a pool table, it ain't going anywhere. It's stable. If you take the same pool cue and balance it, it's unstable. It's going to fall eventually. That's unstable. What's metastable? Metastable is the bar stool. It's going to sit there. It's not going to tip over. But eventually, if you stick around long enough, it's going to fall or someone's going to knock it over. That's what metastable is. So, you can take the measurement of the Higgs mass that we found and calculate its effects on the stability of the universe, which is pretty grand. So here's the mass of the Higgs boson, in units of eV, mass of the top quark, and if you find that the mass of the Higgs boson, the mass of the top quark is in this green area, the universe is stable. If you find it in the red area, the universe is unstable, which means we don't exist. Since we exist, we better not find it in the red area. And yellow, metastability. That means it's pretty stable, but not permanently stable. It's like the bar stool. And where the measurement come in? Right there, in metastable. So what that says, if that's true, is that the universe is not in the final place it should be. It's not in the energy state that the universe is meant to be in. And that means that sometime in the distant future of the universe, what might happen is, instead of having the constants that we have of the universe now, the strength of the electric field, the strength of gravity, the strength of everything, the universe might shift into a different place where all of the constants of the universe are different. And if that happens, well, what will happen is somewhere, and this will happen, if this is true, and there's some argument about this, somewhere very distant, far away from the universe, say, oh, right here, what will happen is, at that point, the laws will change. The universe will go from this higher energy state to a lower energy state. And that bubble will then cross the universe at the speed of light. There will be no warning. That bubble will cross us. And after that happens, the laws of physics will be very different. There will be no stars. There will be no atoms. Because everything will be different. The law of gravity will be different. Everything will be different. Maybe even different numbers of dimensions. Now, I should point out that this doesn't mean that finding the Higgs boson does that. This will happen, or it won't happen, regardless of whether we found it in this heavy-duty. But it tells us something about some interesting stuff. The measurements tell us that we're right near this place where the universe is stable, and that's kind of cool. We're not sure what that means. If this happens, the calculations say it's going to happen long after the sun gets burned out. So I'm sorry to tell you, you have to go back. You still have to take finals. You could do that. Can't get out of that. So, but this is kind of the prediction. Now, I've told you about finding the Higgs by these various experiments. Atlas has looked for the Higgs boson. CMS has looked for the Higgs. And I do have one picture that is absolute proof that CMS has seen the Higgs. And there it is, right there. Peter Higgs was at CMS. And you know, I don't want to make much of this, but there's no similar picture at Atlas. I'm just saying, you know, take what you will of it. Okay, so what's next? Well, there's a lot that's next, and we're running close on time, so I can't tell you too much about it, but I'll tell you a few things. And one of them is huge. It's a really big deal. It's like driving everybody nuts. So, we found this thing that could be the Higgs boson. Let's pretend it's the Higgs boson. What if it is? Well, here's the Higgs boson. This is kind of it wandering through time. And the prediction says that whatever we observe should be the theoretical prediction, the mass of it. This is just the mass. However, the world isn't that easy. There's all sorts of quantum mechanics crap in life. It's tricky. And what happens is the Higgs boson just doesn't sit there minding its own business being a Higgs boson. What happens is the Higgs boson will go along because of quantum mechanics. It'll turn into top quarks and anti-quarks and go back to being a Higgs boson. And, you know, it'll do all sorts of stuff. This is just representative. It'll turn into W bosons and maybe back to top quarks, and then Z bosons, and then maybe to W bosons, and so forth. But the net effect is all these things, what we call quantum fluctuations, takes the observed equals theory and adds this term. And this term says that the observed mass should be theoretical mass of a bare Higgs boson, plus the maximum energy at which the standard model applies, which is, we think is the Planck mass right now, times some terms, which has to do with all this mass stuff. And for those of you who are theoretical physics interns, that's the real messy version of it down there. But we'll avoid that because we don't need to know that much detail. We need to know this thing. So I said that this is the maximum, it's a term that's related to the maximum energy at which the theory works. And that is the maximum energy that the theory works is the Planck scale, which is 10 to the 19th GeV. That is 10 to the 16th orders of magnitude, or not 10 to the 16th, 16 orders of magnitude. 10 to the 16 times heavier than the energy we study at the LHC. So there's where we are. And so let's look at the maximum energy and the mass stuff. Okay? So the maximum energy, if you look down here, I told you I wouldn't have to look, but there's a little square there. So that's the Planck energy. That's the energy at which the standard model is supposed to break down, square it. Turns out to be 10 to the 38, which is a big, monstrous number. This mass stuff over there, that is just the Z boson plus W boson plus Higgs boson, and if you really want to be careful, there's some full orders and whatnot, minus the top quark. So this is the mass caused by the terms having to do with bosons minus terms having to do with fermions. And so this term here, bosons minus fermions, and the maximum energy, when you multiply those two guys together, it has to be really, really small. Because, well, remember we had observed plus theory plus this thing. Now this is a big monster number. So this number has to be really tiny, like 10 to the minus 38. If it isn't, then what we would observe would be huge. So the fact that we found a small mass of the Higgs boson is freaky. There has to be an explanation of this that is natural. I mean, it could be that the universe just is weird this way. We live in a funky universe. That this boson minus fermion thing just happens to be 10 to the minus 38. That's just not the way the universe really works. Usually when you find something really small, it's because it has to be. So there are some options. It could be that this 10 to the 38 GeV thing is wrong. This is not right. And that could be that, well, the standard model doesn't work up to the Planck mass. Maybe at a little bit higher energy we have extra dimensions, in which case the standard model breaks. Or the Higgs boson has stuff inside it, like a proton does, in which case the standard model breaks. I don't know what it is, but this could be wrong. Alternatively, this boson minus fermion thing is equal to 0. And one way to do that is this theory called supersymmetry. Could be right. I don't know what it is. Nobody knows what it is. This, however, is an absolute screaming idea that no matter what, the small mass of the Higgs boson means there must be new physics, and it's in these two terms. And I don't know what it is. Nobody does. So let me tell you what's the future. The LHC ran through December of last year, then we turned on again, and we ran a little bit doing heavy ion stuff. Now we're shut down, we're doing refurbishment, repair, upgrade, and so forth. The LHC ran only about half energy because of some engineering issues, and the idea is that we will run at full energy, hopefully, in a couple of years. So in late of 2014, so 15 months or so now, the idea is to turn the LHC back on and start shaking it down, making sure the magnets work, and blah, blah, blah. Early in 2050, not quite 2 years from now, or less than 2 years from now, the idea is to resume taking data. And we'll run at 13 or 14 TeV, that's the design energy of the LHC. We're currently running at 8 TeV. So what this means, in about 20 months or so, we will be studying a completely new energy frontier, something that's never been explored before. So you could ask yourself, quite fair, what are we going to find when we run at these high energies? And the answer is, well, I don't know. That's crazy. But these are things we're looking for. Supersymmetry, technicolor, explanations, hidden values, black holes, positives, blah, 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 stuff like that. Any one of those things. Or could be we find something totally unexpected. I don't know what we're going to find. But think about this. This is a research place. I mean, we're studying the research frontier. I think actually Einstein said it very, very well. I mean, what he said is, if I knew what I was doing, it wouldn't be called research, now would it? So I don't know what we're going to find, but we're going to look for those things, and it is going to be really cool. You guys are the right age, in a couple of years, this thing will turn on, and God knows what we'll find. It's going to be totally awesome. And with that, we're done. And one little plug, if you want a little bit of science and a lot of smartass, you can do liking on Facebook. I've gotten John Lincoln, and I can put all sorts of really stuff up.
Okay, got time for questions. Lots of questions, I'm sure.
Nah, there's some. If I could ask questions, I have questions. have a question?
Yeah, I have a question.
Yes.
Yeah, what's a fermion?
A fermion. A fermion is any particle that has what we call spin half. So the unit, you've got a unit of spin. So like a unit of weight is a kilogram or a gram or whatever. There is this constant called h bar. It's Planck's constant divided by 2 pi. It's just a number. And any subatomic particle that has a spin of 1/2 h bar, this thing, that's a fermion. Or 3 halves or 5 halves. It has to be something half. A boson is integer, so 0 h bar, 1 h bar, 2 h bar, and those are the differences. It turns out bosons are gregarious, they're like kittens or something. You put all gobs of bosons in the same place at the same time, and they're cool with that. Whereas fermions are like the cats of the subatomic world. They put two together and fight over them. You can't put two fermions, the same fermions, in the same place at the same time. It doesn't happen. And there's lots of sort of complicated reasons why about that. But the interesting thing about that, if you remember for chemistry, you've got Pauli exclusion principle. So you've got your atomic electrons floating around, and in each orbital, you can have a spin down electron and a spin up electron. You can't have a third one because it can only be up or down, plus a half or minus a half. And if you put a third one inside an orbital, then there's 3 of them, and that's just equivalent, going to happen. So it will not let you put another one in there. So the way fermions work explains, well, why atoms are the way they are. And it has to do all with the spin business.
If you had an unlimited budget, you could build any machine you wanted to, what would you build and what would you look for?
Lamborghini, Tesla. Unlimited budget. Well, that's hard. I mean, because the fact is, I get something that allows us to explore the Planck energy. We are studying energies at 10 to the 3 GeV. The Planck energy is 10 to the 19th GeV. So I'd say, forget all this LHC, ILC, sissy crap. I want myself an accelerator the size of the galaxy. Let's go straight for the jugular. But, okay, realistically, I would like to see another hadronic machine, like the LHC, with at least a factor of 10 and preferably a factor of 100 in energy. Because if we don't find something new and bizarre in the next order of magnitude, then it's really, really hard to understand how you can have all this stuff going on. You've got atomic stuff and nuclear stuff and high energy stuff, and then no new behavior, nothing for orders and orders of magnitude of energy. I mean, it could happen, but that's really bizarre. The universe is that way. And so I keep thinking that, it's like you want your kid. You're trying to see on top of your folks' dresser. I just want to stand on tiptoes and see what's up there. And with a little more energy, we can do that. Realistically speaking. But if it's not, money is no budget. A Planck machine and a Tesla.
I kind of have a general question. I kind of have a specific question tied to it.
Okay.
And my general question is, you said that the Higgs boson is like the smallest piece, or like almost like the smallest unit, you could almost say, of the Higgs field. So the general question is kind of, what does that really mean more specifically? And the specific question that's tied to that is, why doesn't that mean that the Higgs boson has, in fact, the smallest mass, and then everything else is just units of Higgs masses, the way we have units of quark charges, right?
Okay, the second one's actually much easier to ask or answer than the first. It is not that, like, an electron has got 15 Higgs bosons sitting on it and therefore it has a certain mass. It is that the Higgs boson, the Higgs boson is not what gives particles their mass. It's the Higgs field. And I will give you another analogy in a minute when I answer the first part of your question. And so in that analogy, it's like viscosity. A particle goes through water, and if it's really slippery, then it goes through easily, and if it's eddy, then it doesn't go through easily, right? And so it gets more mass or little mass, depending on how it interacts with the field. Now, the problem is what I told you there, it's an analogy. So that's what my answer to all of that is, dude, it's an analogy, right? There are many analogies. And so, like the 3 blind men looking at an elephant, one holds the nose, one holds the trunk, and you get different answers. There's another analogy that might be helpful to answer your question. Now, this was back in, 1993 or something. The British, not Prime Prime Minister, the British Science Minister, said, I want to know, what's the Higgs boson? Why am I funding this stupid LHC? You physicists have to write on one piece of, I was going to say 8.5 by 11, but A4 paper about what the Higgs boson is. And so this guy, who was a professor in England by the name of David Miller, came up with this fantastic analogy. And he said, okay, let's think about the Higgs this way. Suppose that all you guys do the Higgs here. We're in a room, okay? So the door on one side, there's a bar on the other side, it's a cocktail party, you're all chit-chatting about your research in the summer or whatever you're doing. And I go on one side, I try to get to the bar. But what happens is I walk across, and you guys are paying attention, and I get to the bar really easily. I don't interact with people. Peter Higgs, on the other hand, goes through the door. He walks through, and you guys are going, or if you doesn't Peter Higgs, Kim Kardashian, I don't care, whoever you think, somebody that you really want to talk to. They're walking through, and you're going like, dude, I want to talk to you. And this guy is never going to make it through the crowd. By interacting with the crowd, his motion is much slower than mine is. And so that interaction with the crowd effectively gave him a heavy mass, right? That's how the field gives something mass. So then you ask what the Higgs boson is. So now we put all the people there together and blow the Higgs, you know what I mean? And what happens is someone goes to the door and they say some rumor like, I don't know, CERN found faster than light neutrinos. Well, except people stop giggling. But then what happens is, then the people near will say, what did he say? And they all crowd and you hear what the rumor is. The people near the door will say, oh yeah, I heard it, and they'll go back to talking to each other. But then the other people over here will say, well, there's something going on. They'll come over and ask what it's about. And these people will drift away. And you'll get this clump in the crowd drifting across the room. That clump in the crowd is what the Higgs boson really is.